So, as you can see, a lot of that kind of left with more questions than answers. So the second part of my REU was trying to answer why. And the method that we implemented was finite element analysis. We built the code in MATLAB from the ground up. And basically how it worked was we took a mesh of the ice shelf. This is the Fimbul. This is a hand-built triangular mesh. And it goes into MATLAB as a bunch of points. So the mesh knows the coordinates of all the different triangles and takes that in. And then we had to drape different data over top of that. This one happens to be ice thickness. The model also needed viscosities and boundary conditions. And then we implemented all that, and it was some basic quote-unquote linear algebra. I haven't taken linear algebra, so I've trusted Dr. Bassis on that. But the output of that is velocities, ice velocities. So this is the Ross, the entire shelf. And just for note, this is the rift that I was showing you earlier. It's flipped 180 degrees because of the way the shelf is and the coordinates are. But you can see that it's shaded for, basically dark blue is 0, and then it gets closer to orange and red as it speeds up. And this result shows that it's fastest right where the rift is. And of course, then the next question is, well, is it fast there because the rift is there, or is the rift there because it's fast there? That's something that we have to keep investigating. But this is the point that the model's at right now. We're getting good results for ice velocity. But what we really want out of that is strains in the ice, which is a simple calculation. It should be a few lines of code, but we just haven't had the time to do that yet. So what's next for the model is to completely finish it, have it outputting strains in the ice. Then we want to start running experiments. We want to start looking at, well, what happens when you have two rifts right next to each other, like in the Fimbul, and one propagates and the other one doesn't? What does that do for the strain fields? What does that do with the forces in the ice? The other thing we want to do is gather more related data to start looking at, because there are basically two theories in glaciology. One says that it's the forces in the ice that cause the cracks to move. The other one says that it's external things like sea level, temperature, humidity, those kind of things, weather. So we'd like to gather weather, and there are automatic weather stations all across the continent, and it's just a matter of talking to the right people to get the data from those. So we're gathering that as we speak. We'd like to look at that because we can either look and say, wow, it was a really warm month in March and they grew, maybe that's why. Or we can look and say nothing was different. And so then we can start looking at something else for causes. We'd also like to expand our image data. The MODIS images were exactly what they say they are. They're moderate. They're okay. The resolution is pretty good, but there are better satellites with finer resolution out there. And we'd like to get those images because we can have a more conclusive data set. We can be able to say, yes, the rift was propagating here and it stopped here. We know this for sure. Because right now with MODIS, it's like, well, we think so. There's a lot of noise, but that's what it looks like it's doing. And then eventually we'd like to, of course, publish our results. What have I learned? Well, I learned basically everything I know about ice shelves and Antarctica. I came in expecting to do a space REU. I wasn't expecting to even be on this planet in terms of what I was doing. So I had to start from the ground up with ice shelves in Antarctica. Dr. Bassis was really patient with me on that. I also learned finite element analysis from the ground up. That was something where we started. There were a good couple weeks where I'd sit in his office and he'd be trying to explain the equations up on the whiteboard, and I probably looked really scared. But we got through it, and once we got out to the other side, it was something where I really understand what's going on, what the code is doing, and all that stuff, which is really cool. Through the programming, I learned a lot more about MATLAB. I came in and I knew that I could program a pretty okay differential equation solver through the programming that I had done, but we really tapped into a lot more of the power of MATLAB through what we did. And above all else, and I'm not just saying this, research is really cool. I really had fun this summer, and I'm looking forward to more opportunities to be able to do this. Doing something that no one else has done before, whether it's glaciers or space weather or anything else, I just think is really cool. So I have my references here. Some thank yous to my advisor, to IT, to everyone that put this together. There were a lot of people that were very patient and very understanding and very helpful. And with that, I'll take any questions anyone has. Yes?
I have a question about motivation.
Okay.
So when ice sheet leaves the grounding line, the ice floats.
Correct.
So then it displaces all its weight in water and sea level, right?
Right.
So why does it matter as much when it breaks off? Because that doesn't change the sea level.
Well, it's a question more of not sea level necessarily with the when they break off. It's more of a, we think that if the ice is flowing faster and they're breaking off faster, that's a sign that something else is changing. Anything else? Yeah.
On some of those exoplots, it looked like the curves would dip a little bit. Did the rifts grow backwards though?
Right. No. And so that's an important point. And we when you look at these, the average one you didn't really see, but this one, yeah, you see that it goes down and up. That's entirely noise in the images. It was something where the images, it was pretty hard to tell, and they were really affected by sun. So like the sun angle, if it was lower, you could really see it was really defined. It would wash it out if it was right up top. And when I was measuring it, it was eyeball, and it was like, well, I'll call it where I can see it, and if it's back a little bit, it's noise. So yeah, the rift definitely wasn't uncracking. It just was noise in the image.
So you took all these data basically manually in like MS Paint or something?
Right, it was Photoshop, so it was a little
Okay.
bit more advanced, but pretty much, yeah. It was. I spent a good 3 weeks just importing these into Photoshop and zooming into about 600% and marking where my start was and going out till I couldn't see the edge of it anymore. And it's actually been interesting because these images, here and later on we got some higher resolution ones. We've been talking to the USGS, and actually Dr. Bassis was talking with some government department about trying to get some declassified spy satellite images, which I just think is really cool. But being able to look at those and see better defined where the rift tip is, you can kind of see, after looking at that, we were like, wow, there actually is a lot of error with the MODIS images once you see closer where it actually is. Anything else?
Yeah, I noticed most of the rifts are generally growing perpendicular to the flow direction of the ice sheet.
Yes.
So, I mean, it looks like it's going to take 300 years or something for any one of these rifts to propagate to the edge of the sheet before it breaks off. But on the basis of history, does anybody know what happens when a large rift gets pretty close to the edge? Do you just get then a huge number of icebergs that break off at one time, kind of catastrophically, or?
Yes and yes, it depends. So
or
like,
does the thing just kind of wear away so that you lose it by the time it gets to the edge?
I'm not entirely sure,
Yeah.
but I would guess from what I've seen and what I know that eventually, and I don't know how long it's going to take because we got a couple images from like 1970, and you can see this one in it, and it's like here.
Yeah.
So it hasn't gone very far.
Right.
And some of the question is, what may happen first is that these two may meet up, and then this whole chunk may break loose before we even get to the edge. It's slow enough moving that that's usually what happens, that the rifts are cracking faster than the ice shelf is advecting. So you get, so for instance, one of the things that we think is going to happen, it's hard to say when because this came out of nowhere, but if you look, and I don't have a very good image in this slideshow, but when this one grew out like this, all of a sudden you're looking at that one and the tip of this one, and you're seeing those are going to connect pretty soon. And then that whole chunk of ice should break loose. So that kind of answers your question, I guess. Anything else? All right, thank you.